All right, we are starting chapter 9 with 9-1, and we're going to translate between various representations of functions. So here's a description of a situation. An amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. This verbal description is useful, but other representations may be more useful. So depending on what the manager needs to do, there are other representations that may help him serve his purpose better. So possible examples are equation, tables, and graphs. So for the equation, his profit is 20 times the number of tickets, so that's a simple equation for him to write. Then this is useful. He can figure out his profit for any number of tickets that he wants. Or he can make a table of various, so if he has common attendances or number of tickets that he sells, he can make a table with the number of tickets and the associated profit he would make with each of these. And then lastly, there's a graph. And again, this is kind of like the equation where you could potentially find any value of profit for a particular number of tickets. And the graph really is related directly to the equation because this gives you your slope and your y-intercept. All right, so these are all used out there in the real world for demonstrating various things, and they're used at different times depending on what you want to do. And as it says, these different representations can help the manager set, compare, and predict prices. So this graph kind of gives trends. This gives you all kinds of flexibility, and this gives you kind of just a very short, detailed picture of things. All right, sketch a possible graph to represent the following situation. So ticket sales were good until a massive power outage happened on Saturday. So we're still at the amusement park. That was not repaired until late Sunday. So if this is our timeline, Friday, Saturday, Sunday, Monday, and things are going along, and then all of a sudden we have the power outage, which said it happened on Saturday, which is here. I don't know, it looks like this is kind of shifted over. It looks like you should probably have this over on Saturday. The power outage happens and then you start to decrease, and then Sunday gets repaired, and then your ticket sales and your profits start to go up. So you could probably reason out what a graph might look like for this situation. Graph showed decreased sales until Sunday. That's the bottom line. All right, so we're going to look at other ways to figure out, if we have data, figure out what kind of function it is, meaning linear, quadratic, etc., and then be able to create an equation for that function and a graph for that function. So remember point-slope form of an equation, y minus y1 equals m times x minus x1, where m is a slope, x1, y1 is a point on the line. This is here, but I don't think we actually use it per se in this presentation, but you may need it for your homework problems if you're trying to come up with the equation for a linear type of problem. This I think is new. It says remember, but I don't believe we've had this year, and you'll see it. It'll make more sense in a minute when I actually go over a problem. First differences are constant in linear functions, and second differences are constant in quadratic functions. So we're going to use this to figure out from a table of data whether we have a linear function or quadratic function. So let's look at what first and second differences are. All right, table shows the height and feet of an arrow in relation to its horizontal distance from the archer. Create a graph. So we got to keep track of everything. We want a graph, an equation, and a verbal description to represent the height of the arrow with relation to the horizontal distance. So here's our data. So remember back in the previous slide, it said first differences are constant in linear functions. So what's a first difference? It means I'm going to subtract this. So I'm going to subtract, actually, it's going the other way. So I'm subtracting in this direction. 6.55 from, or 59.8 minus 6.55. That gives me a value of 53.25. If I subtract 59.8 from 90.55, I'm going to have this difference. If I subtract 90.55 from 98.80, we get this difference, and so on. Subtract this from this, I get a negative value. This from this, I get a negative value. We can see these aren't constant. If this were a linear function, these would all be the same value. So this means, since they're different, this is not a linear type of function. So we're going to try second differences. What are second differences? Well, we're going to take our first differences and do the same thing we did with the height up here. So I'm going to subtract 53.25 from 30.75 to get negative 22.5. I'm going to subtract 30.75 from 8.25, and you can kind of see what's happening. If I subtract this from this, I get this. Subtract this from this, I get this. I actually have a constant second difference, so that means it's a quadratic type of function. All right, so we figured out its quadratic function, so how are we going to get an equation and a graph? Well, we have a table of values, so we're going to do our old linear or quadratic regression that we did a few in chapter 5. So this would be table, or sorry, not table. This is going to be list 1 in your calculator, and this will be list 2. And then we're going to, you enter those into your calculator, and then you go to your stat calc, select quadreg, whoops, and it will generate the parameters for your standard quadratic function. So in this case, your a is negative 0.002, your b is 0.86, and your c is 6.52. Very high correlation coefficient. So this is what your equation is going to be. You're going to plug in your a, b, and c. Once you have that, I mean, you can choose to graph it knowing the with the methods that we learned, or you could just plug this equation into your graphing calculator and graph it that way. And if you do that, when you sketch it in your homework or for a test, just make sure to put some of your key points here, like your max or your min, your y-intercept. We know our y-intercept is right here anyway, but all right, so we have our graph now, we have our equation, our verbal description. You can come up with probably as good a one as the book or I could. The verbal description, the archer shoots the arrow from a height of 6.52, so clearly that's where they're starting. Actually should be 6.55, but quadratic regression is a little bit off. It travels horizontally about 220 feet to its peak. So again, they figured out that 220 and what is it, 98, 99. 99 is our vertex point or our maximum. And then it lands on the ground about 500 feet away. So they found, so I would expect that you would want to mark these points, the y-intercept, this point, and then the vertex. So this is obviously at 500, 0. Okay, so that's an example of from just that set of values we are able to find out a lot about what was going on in that situation. Another example, you get the revealer back up. Janet's rowing across an 80-meter wide river at a rate of 3 meters per second. Create a table. So this time we don't have the table. We have to use the description to write it, to create the table. Then from the table we can write an equation and then graph the distance that Janet has remaining before she reaches the other side. And then lastly, we want to figure out after all that how long before she reaches the shore. So it says 3 meters per second, so she starts at 80 meters away from her destination, and it says create a graph of the distance she has remaining. So when she starts out, she has 80 meters, and then she's doing 3 meters per second, so a second later she's going to have 3 meters less, or 77. 2 seconds later she's going to have 3 meters less than that, and so on. You can probably already figure out whether this is linear or quadratic, but you could use your first and second differences. Obviously, pretty quickly you can see difference here is 3, 3, 3. So our difference is basically that's how we calculated it, was by knowing what the difference is. So it's got a constant first difference. That means it's a linear function. And how do we write a linear equation? Well, it's going to be, you could use point slope form or y equals mx plus b form, whichever way you prefer. So we want the distance remaining, distance at time, and that's going to be equal to, we start out with 80, that's our y-intercept, minus 3 meters times our time. And that's how, so again, it's a little bit different because we're not looking at how many meters we've actually been rowing, but we're looking at how many meters we actually have left. And this is our y-intercept, this is our slope. Once we have those, it's easy to graph. We take our y-intercept, which is at 80, and use our slope, which is going to be down 3 over 1. And trying to see, this is kind of on too large of a scale to see that detail. But you would take your y-intercept and use your slope to create your line. And you can, if you have a good line, you can use your graph to figure out, or we know that when she reaches the shore, our distance is going to be 0. You could solve it algebraically. 0 is equal to 80 minus 3t. Add 3t to both sides and divide by 3. And it's going to tell you 26.67 or 26 2/3 seconds she's going to reach the shore. So again, from just a small description, we are able to do a lot with that information. All right, so let's talk about the differences, the different representations, and what you might do with each of them. So this is translating between multiple representations. This says when you're given the information in this form, you might want to do this. So first one is, if you have a table, we might want to find the first and second differences to see if we have a linear or quadratic. We could graph each as ordered pair and look at the pattern and see if we can determine. So if we got something that maybe looks like this, that's our radical function. If we got something that looked like this, that's a cubic function. So we know some patterns or what some parent functions look like, and we could possibly graph the data points to see if we can match it. And I guess that's basically what this says. I think these two are sort of the same, this one and this one, but match the data to a related paired function if applicable. And then we can perform a regression. So if we know it's linear or quadratic, we could also perform a linear regression on it, though most of the time it's easier just to write the linear equation ourselves. All right, so what if we have a graph? Well, if we have a graph, we might want to match it to a parent function. We can use several points on the graph and put them in a table. And we could use slope, increasing, or constant intervals to write a verbal description. So sometimes it's not. It's a kind of combination of multiple functions, or what is called a piecewise function, just like that power or the profit use. Is it profit or sales from the amusement park, where it kind of went down and then it kind of went up, and it kind of looks a little bit like quadratic, but it was more linear. So it might not have been just a standard function. It might have been a combination of a couple. All right, equation. We can make a table of values from an equation. We could use a graphing calculator then to graph the table values or the equation, or we can make a graph by using transformations of parent functions. So if we know that it's x minus 2 squared. Let's say this is a quadratic that has been shifted right 2. So we know what our transformation rules look like. And then verbal description, try and identify dependent and independent variables and write an equation. So we were able to write the equation of the rowing example just based on the verbal description. Generate a table of values. We also did that. And then sketch a graph using hints from the description about increasing, decreasing, constant intervals, etc. So these are just ideas for you to be able to translate from one form to another. Last thing, I'm going to give you a problem that I'd like you to do. So hotel manager knows the number of rooms that a guest will rent depends on the price. Hotel's revenue depends on both the price and the number of rooms rented. The table shows the hotel's average nightly revenue based on price. And, oops, I guess this kind of tells you. So use a graph and equation to find the price that the manager should charge in order to maximize his revenue. So here's the table. They've already done the first and second differences. So based on that, you should try and write the equation and find the graph and then figure out the price that will maximize the charge, or the amount he should charge to maximize his revenue. All right, so that concludes 9-1. This is your homework. Bring any questions to class.